Hello. This video is meant to accompany a worked example of a physics problem dealing with the stationary states of the infinite square well. Before you read through this worked example and try to solve the problems, it's important that you understand the phasor relationship, the phasor representation of complex numbers, the de Broglie relationship, which is that the momentum of a quantum particle is h divided by its wavelength, or h bar times its wave number k. The Einstein relationship, which relates the energy of a quantum state to the frequency of the state. And the basic idea of the Schrödinger equation and how it works. So if you haven't encountered those concepts before, you'd probably be better to go back to an earlier worked example and get those concepts before you try this one. The idea is to understand the quantum states of an infinite square well. I'm going to skip to the part that I want to focus on for the video, and that is that the solutions to the Schrödinger equation turn out to be sine functions using the coordinate systems in the example. It turns out the solutions are sine functions with this integer n, which is used to enumerate the various quantum states. The quantum states might remind you a little bit of the waves on a string. You've got the fundamental mode of vibration and the first harmonic and the second harmonic and so on. These harmonics are just like the quantum numbers of the states of the infinite square well. Now, what I want to point out in this video is that there's a nice way to understand and to visualize the way these states behave. And so I'm going to flip to a display. Here's a display of the wave function looked at from a particular point of view. And I want to point out that this is like a phasor that's rotating in time. It's like an e to the minus I omega t. And I want to point out that the time-dependent solution to the Schrödinger equation has just such a factor, e to the minus I omega t, this one right here. And this phasor is representing that complex number in the imaginary plane. So the real direction is to the right, the imaginary direction is up and down, and what we're doing is looking at this guy as it spins around with a phase angle e to the minus I omega t. So it's got a frequency of omega. Okay. Now I'm going to rotate this display to show you the actual wave function. Here's the wave function. This turns out to be the n equals 1 state. Notice that it's a sine function as you move from left to right, and at every point in space, this is space here, this is x equals 0, this is x equals plus a, and at every point in space there's a phasor. The phasor is the complex value of the wave function at that point. Let me pop back to the math here. This would be phi 1 of x e to the minus I omega 1 t. That's what we're looking at in the screen. Phi 1 of x is the sine. Here, I'll go back here and remind you of what that looks like. It's the sine of 1 times pi x over a. So when x is equal to a, it's the sine of pi. So it goes to 0 at the right-hand side. Of course, it's 0 at the left because the sine function is 0 at the left. But you'll notice the whole thing is spinning. The frequency of the spin is determined by the Einstein relation. It's determined by the energy of the state. Now, the n equals 2 state is very similar. It looks like this. Notice it's spinning with 4 times the frequency. Every time the ground state goes around once, this state, the first excited state, the n equals 2 state, goes around 4 times. That's because the wavelength of this guy is half of the wavelength of the other one. And you know that the momentum goes like h divided by the wavelength. If the momentum is double, then the kinetic energy, going like p squared over 2m, is 4 times. So you get the idea that this has to be 4 times the energy, therefore it's 4 times the frequency. All right? Now, if I put the two states together, they look like this. You can see the ground state is spinning around at a very low frequency. The first excited state is spinning around at a much higher frequency. The worked example is about the superposition of these two guys. So let me go ahead and show you what the superposition looks like. It's the blue arrows. Now you can see that looks kind of complicated. What I want to point out is that we can go into a frame of reference that's rotating with the ground state. And in that frame of reference, this thing becomes a lot simpler to understand. I've now switched the simulation to show a frame of reference that's moving with the ground state. And you can see that when the first excited state is lined up on the left side, that the superposition is big on the left and small on the right. Let me stop it when that happens. Okay? Here, the first excited, or the n equals 2 state and the ground state are nearly aligned, and the superposition is big over here. On the right-hand side, they're anti-aligned. The excited state, n equals 2, is pointing down, n equals 1 is pointing up, and they largely cancel on this side. And you can see that if you wait around a little while, the first excited state ends up being big on the right and negative on the left, and the superposition is small on the left and very large on the right. So that gives you an idea of how that superposition works. Now there's one other thing I want to point out. To calculate the probability density, let me go back and let this thing turn again. To calculate the probability density, we take the magnitude of the wave function squared. Now the way I represent that in 3 dimensions is to make cylinders. I want to zoom in here and you can see these guys are cylinders whose radius is proportional to the square of the amplitude, the square of the wave function at that point. Okay? I can do the same thing. Let's do the same thing for the first excited state. It looks like this. Okay? You'll notice that when we only have the n equals 2 state, or we only have the n equals 1 state, the probability distribution is stationary. That's why these states are sometimes called stationary states, because the probability distribution doesn't change in time if all you have is n equals 1 or all you have is n equals 2. But if I go to the superposition, you'll notice that no longer is the probability distribution stationary because the amplitude varies with position because these two states interfere with one another. And we get a sloshing of the probability density back and forth. Part of the worked example is to show that the frequency of the slosh is related to the frequency of the n equals 1 and the n equals 2 state. You'll see how that works when you look at the math. All right, I hope this helps clarify what's going on.